Так, смотрю, пока никого нету, кроме нас четверых, да? Саша, а,
Да-да,
я просто не знаю, можно еще подождать некоторое время, а потом начать разговаривать. Вот. Кстати, насчет письма Фану, а, ты спросил у Джинху, как там, что там происходит сейчас? Там Фан на самом
Hello,
деле...
hello, I'm here.
да не,
Э,
нет, Гош, ну это потом отлично, а то у нас идет запись тут, будем сейчас
Не,
письма.
просто тогда, ну просто нужно поговорить будет просто, к чему я, потому что
Ну,
нужно...
поговорим, да, но это не в записи же это делать.
Sorry, Джинху, we just talked about some affairs. Some some things which some
Okay. They're
organizational
talking
matters.
about in Russia. I don't know. Oh, I don't understand what he's talking about.
Yeah. Just sorry for mentioning. I just want to know how it goes in China in Beijing right now. That's more or less what I wanted to know, and also haven't talked quite a long time with Jiran. Just wonder how he's doing. Whether he's teaching a lot or not this year.
He says he changes the topic about the graduation paper.
Oh, sorry, what did you say?
He changed his topic for the graduation paper.
I see. I need to talk to
Okay.
him in any
I
case.
see him because he told me that he faced a lot of difficulty before and cannot find a specific topic to go on, so he changed one.
Yeah, it's really hard to find a proper topic, but I still would like to talk to him, so please let him know that I'll contact him pretty soon, okay, when you meet him.
Okay.
Ну, там в прошлый раз были твои еще ребята,
Не идут, видишь, пока.
Данил и еще.
Да, Илья. Но они, не знаю, что-то их нету пока.
И еще, ну, нет, то я не очень удивлен, потому что тема от них немножко далековата.
Это
Как бы
верно.
я не рассчитывал, да, мы же не рассчитывали, что мы сегодня будем продолжать. Вот,
Да,
как раз
ну просто, видишь, не может сегодня Володя Рубцов, он там
Ну да. Ну, ничего
личность
страшного.
делает.
На самом деле, как бы а, м, мои студенты знают, чем я волнуюсь.
Мгм.
В общем-то, главное я сказал в прошлый раз. Сегодня я уже мог просто рассказать то, что я не успел тогда.
Ну, тогда можно покороче строить разговор.
Ну да.
So whenever you're ready, you can start speaking. You are the co-organizer of the seminar, so you can can decide for yourself. Я думаю, что да, ждать дальше не очень осмысленно. Ну, еще можно до 10 минут, но это уже дальше все.
Ну да, можно начинать. То действительно я могу немножко покороче сказать. И так, может быть, да, может быть, еще твое письмо было немножко неправильно истолковано. Потому что когда ты написал, что я простудился, что правда, я думаю, что все подумали, что, попросту говоря, все отменяется.
Не, я там написал, что мы moved to
Ну
online.
да, но тем не менее, значит,
Да.
как-то логично предположить, что... Давайте я начну потихоньку. Да, и тогда действительно я не буду долго рассказывать, я просто хочу ну, пишу какие-то общие моменты только.
Мгм.
Я не договорил в прошлый раз.
You can share your screen now.
Yes, давай поэтому.
Ты будешь по-английски или по-русски? Я просто не знаю.
Ну, поскольку здесь Джунку, мне придется по-английски говорить. Ну, к тому же мы с ним это делаем как раз, ему это интересно. Как правило, человеку интересно то, что он знает.
Да, это верно.
Павел тоже читает этот текст. Я ему дал знакомиться, поэтому как бы он в отчасти для него, чтобы познакомить его с этим. Ну, а Джунку, просто я как раз сегодня хотел, ну, какие-то вещи, которые ему, конечно, известны, но, может быть, мотивировка или какие-то задачи, которые здесь возникают, могут быть вот, для задачи для дальнейшего исследования, правильно так сказать.
Мгм.
Это всё. So let me share my screen. No. Так, видно вот этот мой планшет, да, вот
Да,
страницы.
хорошо видно.
So I will continue. So today I just want to finish my talk from the last week. And since most of the most important things I have already discussed before, also the details remained hidden, of course, and maybe not so many people are familiar with the parameterization of torsion-free shifts or with moduli. But I mean, the most interesting result, as I can see it now, is exactly this new parameterization of torsion-free shifts on the curves. And well, it is interesting because I expect to get the same parameterization also in higher dimensional case. And then this opens the possibility to answer several questions there which are still open. For example, using this method, we can try to classify all spectral surfaces, or more generally, all spectral varieties which are smooth or normal, calculate more examples, and so on. So and now I'm quite pretty sure that it can be done, but it's a problem for the future. And then next question, the natural question. So let me recall what we have done before. That we have for any operators Q and P from the ring of ordinary differential operators. We have a uniquely defined, non-uniquely defined Schur operator, which has order 0. Such that S, Q, S, S minus 1 QS is equal to D power Q. And so we assume here for simplicity that these are monic operators. That means that the highest coefficients are just 1. And then we can define the P prime, which I will call the normal form. the normal form of operator P with respect to Q. And then we can ask the following questions. What can be said about the form of this operator S? What or at least can we say, can we find it explicitly? So in general, we cannot find it explicitly. Also, in some cases, we can. And of course, it's important to know or to find this operator explicitly, because if we know if it explicitly, then we can explicitly write down, say, the common eigenfunctions of operators P and Q if they commute. Or we can apply this to say something about other open questions. And the same question, what is the form of P prime? So the answers look as follows. Sometime namely when the orders of operators P and Q are coprime, the differential Galois theory so predicts that we can find S explicitly. But in general, it's impossible.
I'm sorry, I don't quite understand. You mean if you have these coprime orders, then Galois theory is applicable, and you can find explicitly.
Then it predicts, and we can find S explicitly. This is because if the orders are coprime, then it's known that the differential Galois group will be commutative. And in that case, differential Galois theory says that the common eigenfunction of two operators P and Q, I forgot to say that P and Q must commute, of course. Then if they commute, then the differential Galois theory says that the differential Galois group is commutative. And then this means that the common eigenfunction of these two operators, which will be defined up to a constant, up to a multiplication on a constant, will be expressed via explicit functions like exponential functions, and this will be of the form of exponential function over some function which has an algebraic geometric nature. Namely, it's an algebraic function defined on a spectral curve. But it's rather, however, it's rather tricky. So to find explicitly this operator is not easy task.
No,
So
the question was a little bit simpler. I mean, is it true that if the orders are co-prime and the operators commute, then you can always find explicitly the operator S, at least in theory, or it is there exists some other hidden.
no,
structure?
it's possible. So it's difficult.
I see.
It's like Krichelev's explicit formula for the Baker-Heiser function. It's of same nature. And so basically you need to, I can add some comment here. So actually you need to solve the equation of the form Qs is equal to S dq. And since Q is equal to d power Q plus some operator of smaller order, then this equation is equivalent to the equation that Q prime S is equal to the commutator of S and dq. And this commutator is just, you can just write down it, so it will be just Q's derivative plus some binomial coefficients, C from Q to I, S I, D I. So it will be of the following form. And on the left-hand side, you will have also some combination of derivatives of S, something like Q Q minus 2 S Q minus 2 plus Q I. So let me denote this coefficient by A. So if Q prime is equal to A Q minus 2 d power Q minus 2 plus blah blah plus A 0, then you can write down explicitly this, apply this operator to the operator S. And put on the right corresponding powers of Q, and then you will get the equality, which is nothing but the usual ordinary differential equation with respect to function S. So S is unknown function. The highest coefficient is 1 here, and this equation will become just ordinary differential equation, but with non-constant coefficients, because coefficients A0, AQ minus 2 are non-constant. But however, if there is a companion equation, namely coming from P with the same trick, then you get two differential equations, and then this differential Galois theory predicts that the common solution of these two differential equations can be expressed explicitly via exponential function of some algebraic function. But of course, to find this function is not so easy. So, I mean, the solution exists and can be expressible even via theta functions in spirit of Krichelev's work, but it's difficult. I mean, it's possible at least. So let me show you one example. Let me show you one example. For example, Wait. Can you see the PDF file? Видно PDF file?
Yes, yes. Yes, we
Ah.
see everything. Yeah, pretty well.
Well, this is a diploma work of Vlad Pulsov, my student, which defended it last year. And this is an example which I showed last time. Namely, we consider the example of such two operators. It's a classical Wallenberg's example of two commutation operators. You must satisfy this KDV equation as in told us last time. And then in this case, since orders are co-prime, it's really possible to find this function explicitly. I mean, this operator explicitly. So by solving these equations and making certain normalizations, we get this explicit form. So this is an example. Do you see that it is rather non-trivial? Yes, it's possible. And in this case, it's even a polynomial, commutative polynomial in the same operators, operators of integration, operators of shift operators. But also there are some rational functions in the variable x. But however, in general, it's not possible. And then, moreover, even if the change screen, okay, so now you can see my my notices, right?
Yeah.
Okay. So this is possible only in Zoom, by the way. I can share several screens simultaneously. In Tencent, it's impossible. Tencent, I would first finish the demonstration and then open it again. Now I can demonstrate several screens simultaneously. And then, yeah. But in general, it's impossible. Moreover, even if S can be defined explicitly, as the inverse operator maybe not. So it's an open question. And this question, whether we can find explicit form of an inverse operator, is also very important in connection with famous Dix-Mézières or Jacobian conjecture. And I will say about it a little bit later. So, and well, all these things are just motivation to study both the necessary conditions on the operator S and also on the normal form in both cases. Either P commutes with Q or not. And so we have two cases. Case one, which was known before, namely if P and Q commute, then the normal form P prime will belong to the centralizer of the operator T power Q, and therefore P prime had the form which I wrote last time, namely it's finite polynomial of some coefficients which are linear combinations of shift operators. Ci are sums of C, I, J, a power J. J
Just
so
stupid
became-
question. Sorry,
Ah.
just a stupid question.
Yeah.
Suppose we have so let Q be equal to 1. Then P is just a centralizer of the the differentiation, right?
If Q is equal to 1,
Yeah, if Q is equal to 1,
yes,
small q, then P is just the centralizer of differentiation, right?
right.
And I thought it was pretty obvious that centralizer of differentiation consists just of all partial differential operators with constant coefficients.
It is true in the ring of full pseudo-differential equation, but in my ring, the centralizer is bigger.
Ah,
So actually, if Q is equal to 1, then there will be no negative part because the highest power of integral is just Q minus 1.
mhm.
It means that it will be just any combination of positive of non-negative powers of D with the coefficients which are linear combinations of shift operators.
Mhm, mhm.
And then, and this normal form, as I told before, can be normalized. And in this case, the coefficients of this normalized form will parameterize torsion-free shifts with vanishing cohomology on the spectral curve. So if we normalize, so this is given by the centralizer theorem. Predicts. So if we normalize P prime, then its coefficients Cij parameterize I forgot how to write this word. Parameterize torsion-free shifts F with vanishing cohomologies on the spectral curve C.
Just one more question, stupid question.
Uh,
I mean, when you speak about parameterization of the torsion-free sheaves, do you mean that you have some kind of modular space of torsion-free sheaves?
yes, exactly. There is a well-known modular space. It is well defined and it is projective. It's projective variety. Well, but no, it's projective scheme. When we speak about varieties, usually we admit that it's reducible and reduced. But even if you can say more generally, in general, it's known that it's projective, and but it can consist of several reducible components, and nothing is known about its singularity, or very few known about the singularity. So it's known that it exists and that it is good enough, but a very little known about the property of this modular space of torsion-free sheaves. Only there was.
Sorry. And in what sense does do the coefficients parameterize this space?
Well,
Do you have some open neighborhood on this space where
exactly. So look, this condition is an open condition. So this condition gives us open subspace. And first of all,
I mean, it's not quite evident this is open. I would say not quite evident this is open. I mean,
yes, it is open.
I mean, usually when you have some algebraic equation, it gives you some closed space, both in Zariski topology and in
But this is vanishing of cohomologies.
Yeah, I mean, I'm not familiar with this.
And so the closed
It's a
subspace.
little bit counterintuitive to whatever I have learned about.
Yeah, but it's just an answer. It's known. So it's that vanishing of cohomologies describe an open subspace. It's known. But well, it follows more or less from same continuity theorem by Grotten. But the question is, well, it's open, but the open subspaces can be very bad. But actually, this normal form, this sequence of coefficients, they are described by several polynomial equations. But this means more or less that this open subspace is just a fine, and this is very amazing thing. So we have a very complicated model space. Inside it, we have an open part defined by this vanishing of cohomology.
So vanishing of cohomology is like general position, right?
Right, but it's more precise condition. It's just vanishing of cohomology. Very short, very precise condition.
To have some non-trivial cohomology, it means you actually have some non-trivial equations satisfied, right? And these non-trivial equations, they give you the risky closed subset, so this is open.
Yeah. But
And you claim
amazingly,
that this space is actually not just a risky open, but is a fine? Did you say that it was a fine?
yes, and it is the most pleasant thing, that it's a fine. Exactly, it can be seen from this normal form, because all these coefficients satisfies several polynomial equations in the fine space. And this is very interesting, because it appears that this open space can be parameterized just very explicitly by some affine set, by the points, some affine set.
So you just coefficients of this p prime, I mean, coefficients that appear in front of shift operators and
Yes,
integration.
yes,
Just numerical coefficients.
yes. So these are just numbers, and this satisfies certain number of polynomial equations. And it is possible to study this model space also in higher dimensions. As I said, I expect many to get many consequences from this simple fact. And moreover, by the way, I can also say, let me return to this example from my last talk. This is the example which I showed before last time. I downloaded it on the blackboard, and this is an example of a normal form. In this example, it's normalized because the normalization for operators of coprime order, the normalization is very explicit. Namely, what can be done? The normalization is a conjugation of our operator p prime with some invertible operator from the centralizer. Any invertible operator from centralizer can be described via the centralizer theorem. And by the centralizer theorem, in this case, it has just two terms, a zero term and -1 term, homogeneous term. And if you look at this example, you will see that we have here the highest power of d is 3. Then there are no powers there are no terms with d square. The next term is with d, and then with constant, and then with integral. And
so what are the coefficients here? What are the coordinates in this expression?
the coordinates here, these are the coordinates which I explained on the blackboard last time.
So are they 2, 1/2, and so on?
We have one, so u0, u1, and u2 are the coefficients of this potential u in its Taylor expansion. So U satisfies the KdV equation, right? What this equation?
Okay, but in any case, what are the coefficients? What are they? You said that this the normal form.
Yes,
parameter
yes. And this is very explicit. Look.
What are the parameters in this expression? What
parameters are U0, U1, and U2. But they satisfy two additional equations, which come from the equation of a spectral curve. So we have three parameters and two equations. So it's one-dimensional algebraic affine variety.
So the wonderful thing is that all the other UKs, which are infinitely many, right? Do not show up in this expression at all.
Yes, exactly. Because this is parameterization only of a torsion-free sheaf. And this is a new way of parameterizing. So this operator is
sorry. What about? I didn't hear that clearly. Well, what about U3, U4, and so on? General UK.
You see, other terms in this case are expressible via U0, U1, and U2, because U, the potential function U, satisfies the KdV equation. So if you substitute this series into the equation, then you will uniquely express U3, U4, and so on via U0, U1, and U2.
Okay. Yes. Can define steadily.
Yes.
Okay. Thank you.
So we know here anything, but it's very well known example. It's a toy example, which, however, shows how it works. Moreover, in this example, this P prime is already normalized because the next term after d power 3 is 0. So we kill next term, and any conjugation with S from centralizer will add some term. Or if you want to keep it equal to 0, then S is equal to 1. So, no other possibility. So for operators of co-prime order, here everything is very nice. Actually, for operators of non-co-prime order, the situation is a little bit more difficult, but more or less it is the same. So there are more difficult normalization, but however, the fact is the same. Coefficients are parameterized in this modular space. And by the way, this parameterization in higher rank is not trivial at all. Last time I already said that if we take just rank 2 torsion-free sheaves on the elliptic curve, then there is an explicit parameterization of such torsion-free sheaves, but it's rather non-trivial. For smooth curves, it comes from the Atiyah parameterization, and they were classified in the work by Atiyah, and then in the work of Priviat and Wilson, they establish a vocabulary between commuting ordinary differential operators of order 4 and 6 and corresponding spectral sheaves. For singular curves of genus 1, it was not known until 2015. And moreover, it's possible to describe such torsion-free sheaves or to parameterize them only with the help of very non-trivial categorical equivalence between torsion-free sheaves and torsion sheaves on Calabi-Yau varieties. And it was done so that this idea was developed in several works by Bourbon and his teacher Drost and other famous articles. And we complete this work, this vocabulary, this parameterization, only in our work with Bourbon. And it's rather tricky. It's quite a non-trivial story. I just want to say that, in this case, the parameterization, to give an explicit parameterization, was possible only for curves of genus 1, it's a singular. But this way, permits to describe this moduli space for any curve of any genus, and independently whether it is smooth or not. So it's really very impressive result. I think this is would be really interesting. Well, and after that, let me continue with my topics. Well, the spectral curve. I forgot to say that the spectral curve is given by the equation. So C is given by the equation f of pq is equal to 0. The equation f of pq is equal to 0 is some polynomial equation. It can be calculated quite explicitly, and this result is pq algebraically dependent virtual Choudhury lemma.
Yeah, I heard this several times, this Virtual-Choudhury statement. So how do you find this f? Do you do this just by induction, by?
No, well, there is very effective way to write down it. Again, via differential velocity.
So it's
Elementary differential algebraic
I see.
or differential algebra. So it can be written. For example, my book contains this receipt, but how to find? But it's a good question, because actually it is very deep. It appears to be very deep, and that I'm going to discuss the next question, which we try to answer with John Paul. How to find PQ? So if the degrees of P and Q are coprime, then this f of PQ, or f of x and y, are just a differential resultant of operators P minus x, Q minus y, where differential resultant is dres is a determinant very similar to usual definition of resultant, but we just need to let me say precisely. So this is a determinant of the following matrix. In the first matrix, we should put the coefficients of P minus x. So namely here something like A00, A01, and so on, A0n. P minus x is equal to A00 plus A01d plus blah, 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 plus A0n, or 0p, better to say here, 0p d power p. So it's the first arrow, then we complete it by zeros. The second arrow, the coefficients of d dot p minus x in the same way. And then at the end, there are zeros. And then you continue until d power q minus 1 dot p minus x. So you multiply these two operators, express their coefficients, and like in the usual resultant, complete these arrows until the end. So the last arrow will go until the end of the matrix. So this
So
coefficient.
don't I understand. When you write A00, is it just a free term without X
Yes,
and without D?
yes,
You only
yes,
take constant terms in front of these.
yes,
Mhm.
yes. And you continue, and then you continue this procedure with another operator. Then you write down here q minus y, then d dot q minus y, and so on, up to d power p minus 1 dot q minus y. And also you add it by 0. So it looks like usual resultant, but it's a differential resultant because you don't shift the polynomials, but multiply it with powers of d, and then calculate coefficients. So it's non-commutative differential resultant. And then the result, there is a not very difficult result from differential Galois theory, says that our polynomial f of xy will be this differential resultant. So it's some sort of miracle that this differential resultant will have constant coefficients. Also, the coefficients of this matrix are not constant, but it appears to be constant. And moreover, in this case, this f will have very specific form. Namely, it will be the form x power q plus minus some coefficient lambda dot y power p plus terms of order less than p dot q. So the highest homogeneous term of this polynomial will be of this form, and it's very important.
I'm sorry, don't I understand. In the way you write it, this determinant is just constant.
No. Not a constant. It's like a resultant, but
No, I mean when you just take constant coefficients A00, A01, and so on without x's.
no. What means constant? They don't depend on x, but well, x means here x capital, some additional variable. But we have another variable x small. So
So they're different. So
aij are functions, in fact. Also bij also functions. So sort of miracle that considering such a matrix,
aij are functions of x capital.
Of x small.
I thought that
X small.
So what is the notion of A00 then?
It's a coefficient of p. So A00, for example, it's a coefficient of p, say p0 minus x capital.
So what is P0 then?
And p0 is a coefficient of differential operator p. The last free term of operator p.
So I don't understand.
The i's are functions here.
AI, why do you write them as A0n?
Because the first index means the first arrow, but I enumerated with 0. 0 arrow. Why with 0? Because this operator p minus x capital is multiplied with 1. 1 is d power 0.
So A00 actually depends on x capital.
Yes. but other coefficients not depend on x capital.
And then second line, do you have something depending on x0?
In the second line, yes.
I mean, but
Yes, it will
partial
not be.
derivative of x0 is either 0 or 1.
If you take d dot p minus x capital, then we will form d power p plus p plus 1 plus p minus 1 d power p plus blah 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 plus d0 dot d
I see. Just
minus xd and then plus derivative of p. Yeah, so the free coefficient will be just the derivative of p0.
P0, yeah, and coefficient at d will contain x.
X, yes, exactly. So x will go right, one term right.
I see.
Well,
But
I repeat that this polynomial, amazingly, this polynomial will have constant coefficients. So it's absolutely non-trivial observation. But it's all known. Moreover, as I said, in this case, this polynomial f will have very specific form. Namely, its highest homogeneous term will be of the form x power q plus minus lambda dot y power p. And Gershon and Chaundi, 100 years ago, probably more than 100 years ago, 1933, show that vice versa, if f of xy has this specific term, has this specific form, and f of p and q is equal to 0, where p and q are some differential operators, then p and q will commute. So now the natural question appears. Is it true in general that is, let f of xy be some polynomial?
so f x y is just this differential resultant.
No, some polynomial. This is a motivation question.
So suppose we have some polynomial
Yes,
form
in two variables, in x and y.
in x and y, in two variables.
Then
X and y.
suppose f of p and q is equal to 0, where p and q are some differential operators.
Not necessarily coprime orders.
Yes. Now of
And the
general.
Borsal and Chaundi, they did this for coprime orders, right?
Yes, for coprime. They prove it only for a very specific form of the polynomial. So if f has this form, then p and q commute, independently whether they are of coprime order or not.
Okay.
But we need a polynomial of very specific form. But the natural question, is it true in general? If you take arbitrary polynomial, and suppose we have a solution of this polynomial in the ring of differential operators, is it true that p and q commute?
I'm just don't going to understand this result of Borsal and Chaundi, because in general, this polynomial will have some mixed terms which will contain both x and y. And
Yes,
if
yes.
you do not commute, how are you supposed to calculate the result of f on x of P and Q on P and Q?
Well, here is assumed that, so what does this mean? This means the following. So we write down our polynomial in certain fixed normalized form.
So it's kind of a normal ordering, yeah? You use some kind of
yes, we just fix form of a polynomial, yeah? And then f of pq is just this linear combination. P power I, Q power J. So the question then says, if this sum is equal to 0, is it true that P and Q commute or not? For specific form of polynomials, this is known already more than 100 years. But for generic form of polynomials, it appears to be a very difficult question. Very difficult question. So we with Junho tried to, first I thought that it's not a difficult question. I thought that we can just apply conjugation. So what we can say, note that f of pq is equal to 0 if and only if f of s minus 1p s minus 1q s is equal to 0. So we can, without loss of generality, assume that we have a polynomial relation between the normal form p prime and d power q, where f is a normal form. But normal form of non-commutative, maybe non-commuting with q operator. Can we come to a contradiction? Can we prove that is it true that p prime belongs to the centralizer of d power q or not? By that reason, we introduced this degree functions, the definition of homogeneous canonical polynomials, and other things which I discussed last time. So this question appears to be very difficult. It's really very strange. Maybe it's connected somehow with Dix-Smith conjecture, but it's not clear to now. So up to now, it's not clear. But what could be done? We could let me now say several results, several necessary conditions, which we were able to prove this. But however, we could not answer this question until the end, up to now, only for certain forms of polynomials, more advanced forms than by Birch-Chardy, but however not for arbitrary polynomials. So the question is open up to now. Very natural question. It's very simple, but it is still open. Let me mention some results which we could prove with Junho. So let me introduce one definition. So we study this Schur operator and normal forms of non-commuting operators. For that, we introduced several definitions, which I gave last time. And let me write down one more. So I say that an operator P from D1 hat sim satisfies condition AQ of K, where Q and K are non-negative integers and Q strictly greater than 1. If the following conditions satisfy. So all homogeneous components, because we are homogeneous components of P, are homogeneous canonical polynomials of Q or T. So it's then PT are totally free of Bj. And let me recall that totally free of Bj operators form a subring in D1 hat C.
So what is PT then?
PT are homogeneous components. So
Oh.
P Pn plus Pn minus
see.
1, blah, blah, blah.
Yeah, I didn't. Yeah, I just
No.
didn't. It's a bit.
Yeah.
I couldn't see this home comp. I didn't realize it. We meant homogeneous component. Yeah, I see.
Yes.
Mm-hmm.
Then the stable degree with respect to A of the homogeneous component equal to the order of P minus I is less than I plus K or any I greater than 0. And then sigma of P, the symbol of our operator, doesn't contain AQIs. And stable degree of sigma of P is just equal to K. Now this is the definition. So if operator P has these properties, we say that it satisfies condition A to P. One property, simple but important property, says that if you have two operators, the one had sim, which satisfy conditions AQ of K1 and AQ of K2, then their product will satisfy the condition AQ K1 plus K2. And then the first necessary condition condition on the Schur operator S says that if S is a Schur operator of Q, which is a differential operator, then S satisfies this condition. Condition AQ of 0, where Q small is the order of Q. Then after that, we could prove some criterion. Criterion is describe differential operators inside the ring D1 hat sim. So the following conditions are equivalent. First, P is a differential operator that is P belongs to D1 with constant highest symbol. Second, for any P greater than 1, P satisfies condition AP of 0, and all homogeneous components PT don't contain AI. And 3, there exists some P greater than 1, such that P satisfies AP0, and all homogeneous components don't contain AI. So this is a criterion describing describing differential operators inside the D1 hat C. And then we get also the second necessary condition for the normal form. Necessary condition on P prime on the normal form of P with respect to Q. I'd say that P prime also satisfies this condition, AQ on 0. So these are necessary conditions which restrict the class of operators, both of Schur operators and of normal forms. And therefore, they give certain information, additional information about operators under consideration. And using these properties, well, these are not all necessary conditions. They are not.
The first necessary condition is that S satisfies AQ0.
Yes, so both S and normal form of differential operators must satisfy this condition AQ0. And the condition AQ0 is very restrictive. You see, all homogeneous components are polynomials with restricted described stable degree. They must be totally free of PG, and also the symbol, highest symbol, should satisfy certain addition conditions. So they are relatively strict. And then we try to study them from the point of view of so-called Newton polygon, Newton region. It's very well known that in Weyl algebra, when you study operators in the Weyl algebra, a very convenient tool to study them are Newton polygons. And in terms of Newton polygons, we could formulate the questions, for example, this Dix-Meer conjecture. We can reformulate in the language of Newton polygons in a very effective way. And since Newton polygons are very effective tool in studying Weyl algebras, we thought that in the same way, the Newton polygons of normal forms of Schur operators could be very effective tool to study normal forms and related questions. So let me explain what are Newton polygons and Newton regions. It's very easy. And then you will see all these properties on the picture. The Newton region or Newton polygon. So what is Newton polygon first? So for students who who don't know yet about its notion, Newton polygons are very nice tools. They are defined for commutative polynomials first. So if you take the commutative polynomials f, x, y, which is equal to sum alpha ij x power I, y power j, the Newton polygon of f is a convex whole of all points ij on the plane such that the corresponding coefficients are not equal to 0. So usually we draw this simple picture. For example, if you take fxy is equal to, say, x cubed minus y squared plus 1, then we should consider all monomials. 1 is a monomial of 0 order, so we draw this point here. Then x cubed is a point here, and y squared is a point here. So the convex whole is just a triangle. It's a Newton polygon. And so very nice theory of Newton polygons in algebraic geometry. For example, I think in the book by Khovansky, a lot of material about Newton polygons is written. It's known, for example, that the number of integral points inside this Newton polygon is a genus of the curve given by this equation. If it's non-singular and if you consider generic Newton polygon of any given polynomial, then it will be a number of integral points inside the polygon will be an arithmetic genus of the curve. So we have a nice geometric interpretation of the notion of genus. For example, in this case, the curve f of xy is equal to 0 has genus 0. It's an elliptic curve. And we can clearly see that there is only one integral point inside this triangle, namely 1, 1. So the genus is 1. Okay. Then we can also say what is a Newton polygon for elements operators from Wade algebra. Let me take an operator from the first Wade algebra. First Wade algebra is just a ring of differential operators with polynomial coefficients. So again, we can write, we can fix the normal form of P, say to write down it again as alpha ij x power I d power j. And then the Newton polygon of P is just the same, namely the convex whole and so on. But of course, in this definition, so when we play with non-commutative operators from Wade algebra, they behaves not so well under some automorphisms or endomorphisms. But both notions of Newton polygon of commutative polynomial, the Newton polygon of an operators from Wien algebra, are used in one approach to try to solve the Dixmier or Jacobian conjecture. Let me recall that the Dixmier conjecture for A1 says that for A1 says that every endomorphism of the first Wien algebra, non-zero endomorphism, is an automorphism. A group of automorphisms of Wien algebra were described by Dixmier. In his famous paper, where he formulated his conjecture. Open, it's still open, very simple but very difficult conjecture. I call it a black hole. It's very dangerous because many people try to solve it because of its simple formulation, but nobody can prove it until now. So nobody knows whether it's provable at all. However, the question is very provocative. And there's analogous Jacobian conjecture, which are closely related. For n is equal to 2, it says that the map f from K2 to K2 given by two polynomials. So f is f1 of xy, f2 of xy. These are polynomials. With Jacobian, which is equal to 1, is invertible. That is, there exists a inverse map it's also polynomial. So it's known, it's also open and has the same nature. It's open after several works by different authors, including Kantsevich, Zheglov, one Japanese guy, Tushimoto, and other guys. They proved that the Dixmuir conjectures and Jacobian conjectures, which can be formulated for any dimension, are stably equivalent. Namely, if the Jacobian conjecture is true, then we can immediately get the Dixmuir conjecture. The inverse direction is not known, but however, many people believe that if we could prove Dixmuir conjecture, then we can prove probably the Jacobian conjecture. But one approach to solve these conjectures is the following. People study possible counterexamples to these conjectures. And let me formulate as an approach to solve these conjectures. Study possible counterexamples. For example, assume we have two operators P and Q in the algebra such that their commutator is 1. Then they give an endomorphism. And then they determine some endomorphism. Psi from A1 to A1, which sends X to P and D to Q. So if they are not automorphism, we can try to say something. Then the result which is known results. There are many people Makar Limanov, this Italian guys, Dixmier, Joseph, many papers about that are written. The people try to say what is the least possible degree, or what is the least possible great common divisor of degrees, or weighted degrees of Newton polygons. So the Newton polygons, if psi is not automorphism, then without loss of generality, of maybe up to composition is an automorphism. The Newton polygon of P and also of Q are of subrectangular type. It can be just explicitly drawn. So X, say X and D. This means that they lie in a rectangular with the vertex A and B. So there must be a vertex at the right upper corner. So they are the following four. We can also assume, without loss of generality, that A greater than B. It's also one of the results of this theory. And moreover, it can be even assumed that without loss of generality, they are of trapezoidal form. Trapezoid dull form. Namely, we can cut the angle. So this is, the angle is 45 degree. The Newton polygon of a counterexample, possible counterexample, must look like this one.
So I don't quite understand. On the left you have rectangle, on the right you have some trapezoid. Is it true that
The right, yes.
the second, or you can actually modify the first?
Yeah, I can modify the first to the most strongest form. So, but the subrectangular type is just easier than this one.
I see.
But this is the most strong result up to now, that it's of trapezoidal form. Moreover, if anybody could prove that we could cut an angle more than 45 degrees, then it will immediately the Dirichlet conjecture fall. So now this estimation is very sharp, but however, it's still unknown. And then the people try to understand what is the greatest common divisor of weighted functions of operators P and Q. So V11 of P is equal to A plus B, and correspondingly V11 of Q is equal to A prime plus B prime. So the Newton polygon will be also subrectangular type with the right upper vertex is equal to A prime to B prime. And in this science, this problem, the best estimation of this great common divisor is 15. So people could prove with a very technical amount of work that if a counterexample that Dirichlet conjecture exists, then this greatest common divisor of vertices of Newton polygons is greater than 15. And the same activity exists also for Jacobian. So it's one of approaches, and people proved this estimation with a very hard analysis of Newton polygons. That was a motivation point for our research with John. And we introduced the notion of a Newton region in the same way of normal forms. Because so there is a hope that if we will study this Newton regions of normal forms, then probably we could deduce some non-trivial consequences, like in these very technical works by many guys about Dirichlet conjecture. But the definition is in the same, it's just the same. So the Newton polygon, so let me give one definition and I will draw a picture. Suppose we have an operator P on the one side C, but we suppose that it satisfies this condition AK of 0. And the order of P is equal to P. Then look at these pictures. These lines, which are the edges of Newton polygon, are called top lines. And in analogy with this definition, which comes from the theory of Newton polygons, we gave a definition that sigma rho top line. Actually, this definition appeared first in the work by Dixon by Dixon. Is a line which goes across the vertex 0p and contains at least two vertices. Is called, so such top line is called a restriction top line. Of Newton region of operator P. So in our case, what is the Newton region? The Newton region is a convex hull of all points on the plane. So we know that P is a sum of homogeneous components, and each of these homogeneous components is a homogeneous canonical polynomial of finite degree because it satisfies condition AK of 0. So we have vertex, the main vertex 0p, and some vertices below that. And because since this operator P satisfies this condition AK of 0, this convex hull looks like this one. So we don't know exactly the shape of this convex hull. But however, a notion of a top line is well defined. Namely, we consider lines which go through this vertex 0p, and such that no points of the Newton region of P lies above this line. So now the question is, what is the possible shape of this Newton region? It appears that it's convenient to introduce the notion of a restriction top line as like this. The restriction top line is the top line which goes at least via two vertices. This is the restriction top line. But in this situation, for generic normal form, there is another notion. So if a Newton polygon always has only top lines because it's finite, it's compact. For Newton region of a polynomial which satisfies, of an operator which satisfies this condition AK of 0, the Newton region is not compact. It's some convex domain, and we don't know much about them. And also, it's possible that the top line can go not via several vertices, but only via one vertex, say, and looks like an asymptotic line in analysis. And I am almost finished. let me say somewhere there. I continue the definition. So in this definition, if P doesn't have the restriction top line, but there exists a top line. A top line means that there are no vertices above this line. Yeah? There is a top line at 0 of the form sigma x, sigma 0x plus y is equal to p, where sigma 0 is greater than 0, such that for any sigma greater than sigma 0, the line L sigma x plus y is equal to p is not a top line, then L0 is called an asymptotic top line. For generic differential operators, we can find an example of an operator whose normal form has an asymptotic top line. In this case, this top line goes through this vertex 0p, and the other vertices asymptotically tends to this line, but no more vertices except this one lies on this top line. This situation is possible. And then the result says that if P is an operator satisfying this condition AK of 0, then one of the following conditions hold. So first, the stable degree of A of P is equal to 0. And this is equivalent to say that P is lies from the centralizer of P power K. The second, the stable degree A of P is greater than 0. And then and P has a restriction top line. And third, the stable degree of A of P is greater than 0, and P has an asymptotic top. So I need to say that all these notions, or the notion of a restriction top line and of asymptotic top line, are well defined. They are unique. It can be proved, and also we can, by many technical work, we can prove basic properties of top lines like the Dix-Nier paper. But it's boring. Just say that. But you see, we have only three possibilities: either P is from centralizer, or P has restriction top line, or P has an asymptotic. Well, we could prove the following theorem. So, theorem: if P and Q are differential operators, and the normal form has a restriction top line, And this means that the stable degree is greater than 0, so it's not from centralized. Then there are no algebraic relation between P and Q. So this is one of partial cases answering the question, this simple question about. And for some polynomials in the asymptotic case, the question is still open. We could prove only for some specific polynomials. So in general, we cannot prove it. We cannot say if it's true or not. But for certain form of polynomials, or in the case of the normal form, as a restriction top line is possible to prove with the help of certain combinatorics and techniques which studies these Newton regions, this result. Well, the good question why it's so difficult. Perhaps there is some hidden connection with the Dixnier conjecture, but it is. And then, well, other open questions in this direction by using this analysis of Schur operators and normal forms. It's interesting to analyze other open problems, the theory of commuting differential. For example, we could try to find more examples of commuting operators in the Weyl algebra, because so little is known about them. There are many beautiful results found before by Mironov and his pupils, but up to now, the generic form, or generic theory of commuting operators from Weyl algebra is still old. Another application is the application of the theory of normal forms to study of difference operators. We could get something with another student, with Sergei Fitmilyak, by studying the new examples of Mironov and Mauleshov. This theory of normal forms can be extended to the case of difference operators, and it appears that, say, in their examples, and Mironov's and Mauleshev's examples, the normal form of their new examples coincides with normal forms of ordinary differential. So probably using the theory of normal forms, you could get more examples in that direction. So I finished my talk with many open questions and many challenges. Maybe it will be interesting for you, and I hope I could explain, give a review of certain approaches in this science. Both conjectures, all questions about Weyl algebra are very deep and very difficult. And of course, by that reason, they are very difficult, and it's difficult to say something. But however, we still can do something in that direction. So I'm finished. Thank you.
Yeah, thank you. It was been very interesting, a little bit technical, but I believe all interesting things should be technical at first.
Yes, you see the most, the question is very simple, very basic. Look, Dixnier conjecture itself is very simple, but extremely difficult. It's open and it's a price conjecture. Anybody who could prove Dixon conjecture will get immediately a big prize.
I
The
see.
question about the polynomials, you can see it on the right hand side. This small innocent question whether the polynomials commute if they satisfy some algebraic relation is still open, even for well algebra, but not only for differential operators.
Yeah.
Why it's so difficult, I have no idea. Just a coincidence. But probably there are some hidden connections in Dixon conjecture. I don't know. I feel that both conjectures, I mean Jacobian or Dixon conjecture, like real black holes.
Yeah.
They're really simple to formulate, but unbelievably difficult to get something. Maybe
should avoid them by all.
Yes, because they could
Not
be
to
the
get sucked
same.
into it. Okay.
Okay. Well, if there are more questions, then please ask me. If not, then
okay. Well, as far as I'm quite satisfied, I have no other questions. Maybe some of our Jan participants.
I say to students that I tried to invite the main specialist in this activity, Makar Limanov, to make a review talk about it. It's near or Jacobian conjectures, but unfortunately he refused because of sanctions. It's a pity. But well, I could at least give a small review instead.
Okay.
Yeah.
Maybe we can invite him later. Maybe
So what kind of section is that?
Well, you see, the sanctions of West countries against
it's political. I mean, there's all this
political sanctions, because in many Western universities it's forbidden to participate in Russian conferences, and it's also forbidden to participate.
Collaboration sometimes are forbidden.
Yeah, collaboration is forbidden, and also even talks at seminars are forbidden. For example, in England, as far as I know, anybody who could try to give an open talk somewhere in Russian, even online seminar, they can be banned there. So it's not. It's not
too strict.
Huh?
It's too strictly.
Yes, it's too strictly. But you see, today I tried to download the tech package, which you use in your tech file. And I was unable to do that. Before I had no problems. But I think it's also a corollary of sanctions. Perhaps LaTeX or MIGTeX.
It's strange because I use Overleaf and it's free and there is no.
Yes, but me too. But today, no server was available in Russia. No, at all.
Overleaf is free. Overleaf. Again.
Well. But I have this my tech editor on my own computer. Usually, when I use some extra package, I just downloaded it for free from one of hundreds sites abroad. But today, this procedure just didn't work at all. Perhaps I need to try VPN connection, but however, I was very surprised that Tech also banned its support.
Well, yeah, it's actually when I tried to apply for some, visit program in Australia last year, I was banned unless I used VPN.
Yeah.
Okay. Any case, let's not, sigh now. We need to wait for it to change. So next time, I think we'll have we'll have Volodya Rubtsov speaking about some integrable systems. And as far as speakers beginning with the 12th of March, I still don't have any ideas. So if you have any suggestions, anybody who can and want give a talk, just let me know. I'll try to invite.
Okay. Okay. Yeah, I can try to invite some Spain mathematicians which can give a talk about differential dollars and related things. But again, I'm not sure that they will not refuse my invitation.
Well, in Europe, it depends on the country, actually. The England is
That's
kind
right.
of extremal situation, and other continental Europe is not that bad. At least, at least in France, so far it's not been forbidden, at least to collaborate. I know many examples of collaboration in France, and even people trying to go to IHS. They invite people from Russia. The problem is to get French visa. That's actually a hard thing to do, but as far as
Yeah.
IHS are concerned, people can go there. Okay,
Okay.
so see you next Tuesday, either in
Yeah.
person or virtually. And I'm happy to see Jiran here. I hope we can
Yeah.
continue talking later.
Yes, yes.
Okay. See
I'm
you.
happy to see him too.
Uh,
Okay. Anyway, bye.
Bye.
Goodbye.